Welcome to Quantum, where physics meets philosophy and mathematics shapes reality. Today, we journey to the boundary between quantum mechanics and topology, explored through 4 segments: a review of the integer quantum Hall effect, disorder and the emergence of localized versus extended states, edge chiral modes and the boundary bulk interplay, and an introduction to the fractional quantum Hall effect. Integer quantum Hall effect. The integer quantum Hall effect, IQHE, refers to the phenomenon where the Hall resistivity becomes quantized, taking on discrete values determined by an integer filling factor nu, which counts the number of completely filled Landau levels. The underlying physics of the IQHE is governed by the Landau problem, where electrons are treated as free particles subject only to Pauli's exclusion principle. Notably, the Hall resistivity exhibits distinct plateaus, each corresponding to an integer value of the filling factor over a finite range of magnetic field strengths. On each plateau, the longitudinal resistivity vanishes. The stability of these plateaus arises due to the presence of disorder or impurities in the system. Disorder, localized and extended states. Disorder is modeled as a random potential that lifts the macroscopic degeneracy of Landau levels, effectively broadening each Landau level into a band. As a result, many of the electronic states become localized and do not contribute to electrical conduction. In disordered systems, 2 types of states emerge: localized states, found near the edges of the Landau bands, which do not transport charge; extended states, located near the center of the bands, which do carry current. These states compensate for the charge not carried by the localized states. As the magnetic field or carrier density is varied, the Fermi energy sweeps through these states. When it lies within a region of localized states, the number of current-carrying extended states remains unchanged. Consequently, the Hall conductance remains constant, forming a plateau, and the longitudinal resistivity stays 0 because localized states cannot facilitate scattering between the edges of the sample. Only when the Fermi energy reaches another group of extended states does the Hall conductance change, producing the next quantized step. In summary, extended states are responsible for carrying current and determine the quantized value of the Hall conductance. Localized states are non-conducting and responsible for the robustness and stability of quantization. They ensure the formation of plateaus by insulating the system against small variations in external parameters. Edge chiral modes. In the classical picture, electrons moving in a magnetic field follow circular cyclotron orbits due to the Lorentz force. At the boundaries of a conducting material, these orbits are truncated by the physical edge, resulting in a skipping motion along the boundary. This motion confines electrons to travel in a single direction along the edge, making them effectively chiral. At opposite edges, the chirality is reversed, leading to a net zero current through the bulk but allowing current to flow along the edges. This classical intuition is confirmed quantum mechanically. For each filled Landau level below the chemical potential, there exists 1 chiral edge mode per edge. Therefore, if n Landau levels are filled, there will be n chiral modes propagating in the same direction on each edge, with each mode originating from 1 Landau level. Although individual edges may host purely chiral states, the system as a whole remains consistent with the Nielsen-Ninomiya theorem, which requires equal numbers of left and right-moving modes in one-dimensional systems. Indeed, the theorem's constraints do not directly apply to one-dimensional boundaries of two-dimensional systems. As a result, chiral modes on one edge are counterbalanced by antichiral modes on the opposite edge, ensuring that the total chirality of the system remains 0 as required. The essential conclusion is that in the quantum Hall effect, current is carried entirely by the edge modes. The bulk Landau levels are flat and completely filled, contributing no net current. While localized currents may exist within the bulk, their contributions cancel out overall, rendering the bulk insulating. In contrast, the edges act as perfect conductors due to the presence of unidirectional chiral modes. Fractional quantum Hall effect. The fractional quantum Hall effect, FQHE, discovered in 1982, is a remarkable quantum phenomenon in which the filling fraction nu takes non-integer values. The first experimentally observed plateaus occurred at nu equals 1 over 3 and nu equals 2 over 3 in the lowest Landau level. Electron-electron interactions play a central role in the physics of the FQHE, in contrast to the IQHE, which can be largely understood as a single particle effect. Of particular importance is the Coulomb interaction, which is typically treated as a perturbation. However, due to the macroscopic degeneracy of the unperturbed Landau level, this is a case of degenerate perturbation theory, involving an extremely large perturbation matrix. In the FQHE, all physics occurs within a single Landau level, yet many body correlations, driven by interactions, open new energy gaps at specific fractional filling fractions nu. These interaction-induced gaps give rise to a rich structure of fractional quantum Hall states. Unlike the IQHE, where the gap originates from Landau level spacing, the FQHE gap emerges purely from many body effects within the same Landau level. Localized versus extended states play the same role in the FQHE as they do in the IQHE. When interactions create a gap at a fractional filling, the introduction of disorder leads to the formation of localized states within this gap. As in the integer case, these localized states do not carry current, while the extended states do. This results in quantized Hall plateaus and vanishing longitudinal resistivity, replicating the key phenomenology of the IQHE, but now arising from interaction-driven physics. Conclusion. Thank you for watching Quantum. Until next time, stay curious, stay critical, and keep exploring the edge of physics and philosophy.